Okay, so today is talking about atoms and chemical formulas. We'll try to get through this quickly. Essential question for today's lecture is how can we use the periodic table to identify the atoms within a chemical formula? And how can we identify the number of each kind of atom within a chemical formula? So reviewing matter, this is stuff we've talked about before, so you should know these things. Atoms are the smallest form of matter and make up elements. Elements are made of a single kind of atom and are represented on the periodic table. When more than one element combines, it creates a molecule. And when a molecule is made up of more than one kind of element, it is called a compound. So guys, remember that every substance is made of atoms. Um, all how did I put this before? So not all molecules are elements, and not all molecules are compounds. All compounds are an element. All compounds are a molecule, but not all molecules are compounds. That's what it was. So some molecules are elements, some molecules are compounds, but all compounds are molecules. Hopefully that makes sense. Okay, so chemical symbols our elements are represented by a chemical symbol. They always begin with a capital letter and sometimes have a second lowercase letter. We've already talked about this again. The element iron has a symbol Fe, which comes from its Latin name ferrum. And the element phosphorus just has a symbol P. So as I talked about in the other video, the ones that have letters that don't really go with their words, like gold is AU, silver is AG, those names are usually based on the Latin name because those were all elements that people in like the BC times could dig up out of the ground, and they didn't have English words for that yet because English didn't exist yet. So yeah. Periodic table, we talked about this last week. Periodic table tells us more than just the chemical symbol. It's also organized to help us understand, not sure why there's a hyphen in that word, help us understand how elements will combine to make compounds and molecules. So you can get all kinds of information from the periodic table, how many electron shells it has, how reactive it is, what family it's in, what type of element it is, if it's a metal or non-metal or metalloid, and then also how they kind of combine with other things. So as far as we are concerned, there are three different classifications on the periodic table. We will go into this more in our next topic. So metals are all these light blue ones. Metalloids are the purple, and so they are along the line where metals and nonmetals meet. And so that's why their color is a combination of the two, because they have properties that are a little bit like metals, a little bit not like nonmetals. And then all the nonmetals are pink. So if you see the metalloids are a combination of the blue and the pink, because they're a little bit like each of those. And like I said, we'll go into that next week. So more classification, metals have a tendency to bond with nonmetals to make compounds. So sodium, which is a metal, combines with chlorine, which is a nonmetal, to make salt. Hydrogen and oxygen are both nonmetals. That's not a good example. Magnesium and sulfur combine to make, different compounds. So they tend to combine. Nonmetals will also combine with other nonmetal atoms to make molecules. So this is like water. Hydrogen and oxygen are both nonmetals. They combine to make water. Have you ever noticed that there's a small 2 following hydrogen in the chemical formula for water, H2O? And we're going to talk about what that means. You probably already know what that means, but that's okay. So why do elements make molecules? Like, where do these things come from? Atoms of elements retain their nucleus, but electrons can be transferred or shared. So when elements combine into compounds, the core of them, the nucleus, stays the same, but those elements that are floating around the outside, they tend to do different things. They want to attach to each other. They want to pop off and go to a different place. Electrons are tricky, so they do different things. Atoms form ions, the negative or positive charge. And we will talk more about ions and how they are bonded at the end of this unit. The transfer and sharing of electrons with another element's atom is known as a chemical bond, which creates compounds. So when we have two elements and they combine with each other to make a new substance, there's a bond that joins them together. And like I said, we will learn at the end of this unit, there's two different ways they do that, and we'll talk about what those are in a week or two. So the periodic table and compounds, the periodic table helps predict ion formation and charge since atoms tend to gain or lose electrons to resemble the stable group 18 elements. So I think you guys learned this on the periodic table. Group 18, that is that column on the very right-hand side of your periodic table, and they're called the noble gases. And those elements don't really react with anything. Krypton, argon, helium, they have a full electron shell, so their outside layer of electrons is full, and so they are happy campers. They don't want to change anything, they don't want to hang out with anybody, they are good on their own. And other elements want to be like them. They're like the popular kids they look up to and want to be like, and so they try to, start acting like them. So metals tend to form cations with positive charges, and nonmetals generally form anions, and they have a negative charge. And again, we will talk about what that means here later. So chemical formula, the different elements that make up the compound are represented by their symbol in a chemical formula. For example, water is made up of hydrogen, H, and oxygen, O. Its chemical formula is H2O. Okay. This question is asking, how can you tell the difference between a chemical symbol and a chemical formula? So a chemical symbol will only ever have one capital letter, and a chemical formula could have, 10, 12, 15 capital letters. It will have multiple capital letters, and it might have some numbers in there. Elements will only ever have one capital letter, which is the chemical symbol. Chemical formula. In the example of water, H2O, a small subscript follows the hydrogen, H. And this is because chemical formulas are expressions that state the number and type of atoms present in the molecule. So I always say the chemical formula is like the recipe for your molecule. It's going to tell you the ingredients, which are the elements. So for water, our ingredients are hydrogen and oxygen. So we know if we're going to make water, we need 2 different ingredients. But then it also tells us the amount of each ingredient. So if you're making a cake, you know that you need flour and sugar and eggs and salt or whatever. But you also need to know how much. Like you're not just going to start randomly putting in flour and sugar and eggs till you feel like it looks good. You're going to follow a recipe with certain amounts so that it mixes right. And so the chemical formula, it's going to tell us how many oxygens we need, which is 2 because of our subscript, and how many oxygens we need, which is 1 because there is no subscript. So if there's no number here, that always means 1. If it was 0, they just wouldn't put that letter in the formula. So like here, we don't have any phosphorus in this formula because the P just isn't there. So if the letter is in the formula, that means there's at least 1 of that atom. So why do scientists use stick and ball models similar to the ones below to represent chemicals? What do you think? Like, why would they use something like this to show us what compounds might look like? What do you think? There is an order to each chemical formula. When a metal is present in a chemical formula, you'll see it written first. That's good to know. So like in salt, NaCl, so sodium chlorine. The sodium goes first because that's a metal. Chlorine is a nonmetal. It goes second. Counting the elements. So this is another thing you can do. So again, you need to know which elements, like what ingredients you have, but then you also need to know how many of each element you have. So to determine the number of elements in a chemical formula, look for the chemical symbols. And there's a hint. Every element only has one capital letter in its symbol. So glucose is this chemical formula. It's a sugar. That's what makes like fruit and cake and stuff taste really good. So that is regular sugar. And since there are 3 capital letters, we know that glucose has 3 ingredients, carbon and hydrogen and oxygen. So those 3 things combined make sugar. And then table salt, we have sodium, which is Na, and then chlorine, which is Cl. Again, that's an L, not an I. And so we know there's 2 elements in this. We have sodium and chlorine. But then again, since there's no subscripts here, we have 1 sodium, 1 chlorine, and that's it. So let's talk about the subscripts. I've mentioned this a couple of times. So subscripts are the small numbers after the element's chemical symbol in the chemical formula. The subscript follows the atom it represents in the chemical formula. Again, if there's no subscript, it is understood there's only 1 atom of the element. So again, there's not going to be elements listed if they're not in that formula. So here it says, which element does the subscript represent in CO2? So this little 2 here Does that mean there's 2 carbons or 2 oxygens? It's 2 oxygens because the 2 goes directly with the element that it follows. If there was more than 1 carbon, there would be a number between the C and the O. But since there's no number there, there's 1 carbon and 2 oxygens. We're going to skip this part. Subscript. So O2 tells you that there are 2 atoms of oxygen. H2O tells you that there are 2 atoms of hydrogen and 1 atom of oxygen. So even though this is an element, it is one type of atom, so there's only one capital letter, this is still a molecule because it has 2 of those atoms combined together. Oxygen reacts with a lot of things. So you'll see oxygen in many, many, many chemical formulas. Oxygen gets around. So counting the atoms. So let's use our earlier examples to see how subscripts show the number of atoms for the element. Remember, the lack of a subscript means there is only 1 atom of the element. So if you remember in glucose, we had 3 elements. We had carbon and hydrogen and oxygen because there are 3 capital letters. So how many carbons are there? There are 6 carbons in glucose because it has the 6 directly after the C. There are 12 hydrogens because this 12 comes directly after the H. And there are 6 oxygens because the 6 comes directly after the O. So in a molecule of glucose, there are 24 different atoms. It is a big, big old molecule. So it's very complex and it tastes delicious. There are 24 atoms in one molecule of glucose. And then again, like I was saying earlier, table salt, so just regular salt, sodium chloride, there are no subscripts. So there's 1 sodium, 1 chlorine. Because if there's no number, it's 1, because again, they wouldn't put in an element if it's not in the compound. Scientists are all about saving time. So this is what I was just saying. So to find the total number of atoms in a chemical formula, identify the number of elements present, use the subscripts to determine the number of atoms for each element, and then add up all the elements together. So here there's 6 C's, 12 H's, 6 O's. There's 24 total atoms in this molecule. Table salt, there's 1 Na, 1 Cl, there's 2 atoms total. So table salt is a very small molecule compared to glucose. It's only got 2 atoms, where glucose has 24. It's a lot bigger. Okay, so let's just look at one of these real quick. So here we have C2H4O2. So how many carbons are there total in this molecule? 2. How many hydrogens are there? 4. And how many oxygens are there? 2. So there's 2 carbons, 4 oxygen, 2 carbons, 4 hydrogen, 2 oxygens. So this molecule total has 8 different atoms. Okay. Here we have C4H10. There's 4 carbons in that one. There's 10 H's. This total molecule has 14 atoms. So it's a little bit bigger. The chemical formula for sucrose is C12H22O11. So use your knowledge of atoms and molecules along with these models shown below to describe an atomic model of 3 molecules of sucrose. So how many atoms of these elements are there in sucrose? So sucrose is another type of sugar. Sugar is really popular because it just has tons of different atoms in it. So we have carbon and hydrogen and oxygen. How many carbons are there? 12. So you would have 12 of these little gray guys. And then hydrogen, there are 22 of them. So hydrogen are these blue ones. They're little. So you have 22 of those. And then oxygen there's 11 oxygens. So you'd have 11 of these. So the model for sucrose would be really big because you would have 12 plus 22 plus 11. So 12 plus 22 is 34 plus 11 is 45, right? So the chemical or the molecule for sucrose has 45 atoms in it. That is a big old molecule. And again, very tasty. So let's pretend you're an atom. What? If your birthday is in the months of January through June, you'll be an aluminum atom. If your birthday is in the months of July through December, you'll be an oxygen atom. Okay, so this is something you would need to do in person. So my birthday's in March, so I would be an aluminum atom. And let's make an aluminum oxide Al2O3. Your compound will need 2 aluminum atoms and 3 oxygen atoms. So basically, you would need to find 2 people who had birthdays in the first half of the year and 3 people that had birthdays in the second half of the year to come together and make a molecule. So I would be an aluminum. I would need 1 other aluminum and find 3 people who were oxygens. You're not in class right now, so we're going to skip this part. Hopefully you get what would have happened. So sometimes chemical formulas will have parentheses, and this formula means aluminum is bonded to a molecule of sulfur and oxygen, and the subscript outside of the parentheses applies to all the elements in them. So this is just math, okay? So if you guys have ever done like a parentheses with a number outside, so like 3 times, I don't know if you guys are doing algebra yet, x plus 2 or something. The 3 applies to everything inside the parentheses. So here, the aluminum, we have 2 atoms of aluminum, and then separately, I mean, it's all connected, but it's separate. We have this molecule, SO4, so sulfur, and then 4 atoms of oxygen. So each of those little sections has 1 sulfur, 4 oxygen. But we have 3 of those. So we have our Al2 over here, and then we have an SO4, an SO4, and an SO4. And somehow they are all combined. So because let me see, where is our Al2? Oh, they're separate. That's okay. So we have those 3 separated. Because there's 3 of those, we have an SO4 over here, an SO4 over here, an SO4 over here. So technically, we have 3 S's and 12 O's in the whole thing. So this 3 gets applied to the S, and it gets applied to the 4. But because there's already 4 O's in here, we have to multiply the 3 times the 4. So the 3 gets times by the 1 that's here next to the S, and the 3 gets multiplied by the 4 that is by the O. So you have 2 aluminums, 3 sulfurs, 12 oxygens in this whole model. Okay, so make sure the subscript always goes next to the one that it's with. If it's outside the parentheses, it goes to the entire thing inside the parentheses. Notice the 3 does not go or does not affect the aluminum. It only affects the sulfur and oxygen because that's the only thing inside those parentheses. All right, so we're going to practice counting a couple of these, and there are some on your paper as well. So here we have barium, and then we have nitrogen and oxygen. We have 3 oxygens. So how many bariums do we have? 1, because there's no number, it's just got 1. How many, inside the parentheses, how many nitrogens do we have? We have 1 nitrogen, and we have 3 oxygens. But again, we have 3 of those separate molecules. So we have an NO3, an NO3, and an NO3. So technically, we have 3 N's, because 3 multiplied by the 1 that's not here. So 3 times 1 is 3, so 3 N's. And then we have 9 oxygens. So there's 3 times the 3 to get 9 oxygen. So in this entire whole compound molecule, we have 1 barium, 3 nitrogen, 9 oxygen. Okay, let's do this one because it's a little bit complicated. So our parentheses are first, and that's okay. So here we have 1 nitrogen and 4 hydrogens, but we have 2 of that entire compound. So the 2 gets multiplied by the 1 next to the nitrogen. So we have 2 nitrogens, and the 2 gets multiplied by the 4 by the hydrogen. So we have 8 hydrogens. So 2 nitrogen, 4 hydrogen, 2 nitrogen, 4 hydrogen. That's hard to say. But then we have 1 sulfur here. So again, there's no number, but there's also no parentheses. So it's just the 1 sulfur and then 4 oxygens. So this entire big molecule has 2 nitrogen, 8 hydrogen, 1 sulfur, 4 oxygen. So hopefully that makes sense. Look at your subscripts, look at your parentheses, multiply everything inside the parentheses by the subscript outside of the parentheses, if there is one. We'll practice with these a lot. Okay, so to find the total number of atoms to elements in the parentheses. So use a subscript inside the parentheses to determine the number of atoms, and then multiply each of these atoms by the subscript outside of the parentheses. So here we have 2 atoms of aluminum, that's separate. We have 1 sulfur inside and 4 oxygen inside. So for each of these, 1 sulfur, 4 oxygen, but we have 3 of these whole things. So the 3 gets multiplied by the 1, so there's 3 there. The 3 gets multiplied by the 4, so there's 12 there. So total, we have 2 aluminums, 3 sulfurs, 12 oxygen. So 3 of these, 3 times 1 is 3, 3 times 4 is 12. Coefficients are a whole other thing. So coefficients are the big numbers at the beginning of the chemical formula. So that tells us that we have 2 of these entire molecules. So you may have multiple things inside the parentheses, which are like little bits inside that molecule. If you have a coefficient in the front, then you have 2 or more of the whole molecule. All right, so you may have a 1 whole sucrose here and 1 whole sucrose here. And they play a role in counting the atoms. So, however, they represent the number of molecules, meaning they represent all the elements in the molecule. And they're important when balancing equations, which you guys will get to in 8th or 9th grade, I think. So let's do subscripts and coefficients together, and this is where things get a little bit more complicated. So to find the total number of atoms in this formula, this is hydrogen, sulfur, oxygen. So we're going to use the subscripts to determine the number of atoms. So in one molecule of this compound, don't worry about the 2 yet. We're just going to worry about one molecule of this compound first. We have 2 hydrogens, we have 1 sulfur, and we have 4 oxygens in just one of those. But then this big 2 tells us that we have 2 of those compounds. Now we're going to look at the atoms for the whole thing of both compounds or both molecules combined. So we take the 2 times the 2, and so total we have 4 hydrogens. The 2 times the 1 for the sulfur. So again, in the whole thing we have 2 sulfurs, and then 2 times the 4 for the oxygen. So in the whole thing we have 8 oxygens. So your total amount in this formula is 4 hydrogen, 2 sulfur, 8 oxygen, because your coefficient gets multiplied by the subscript for each one, okay, like this picture is showing. Using the atomic models provided, predict whether the chemical formula will include subscripts, coefficients, or both, and explain how you know. So we can just go through these quickly. So this one has 3 of the same one. So this one is going to have the subscript of 3. This is just one type of atom. So this one will have no subscripts, because again, if it's just one, you just write the letter. And then this one is going to have both. It is going to have a coefficient of 2, because you have 2 of these molecules, 1, 2. But then it's also going to have some subscripts, because each molecule of this compound has 4 of whatever this purple ball is. Okay, so it's going to have 2, say sulfur, 2s4, there's 4, and then maybe O1, because each molecule has 1 oxygen. Okay, so this one's going to have coefficients and subscripts, because we have 2 individual molecules, and then each molecule has 4 of that one type of atom. Lordy. Okay, so here's what happens when you have subscripts, parentheses, and coefficients, when you have all of it combined. So to find the total number of atoms of elements in parentheses, do these things. Use the subscripts inside the parentheses to determine the number of atoms. So you're going to look at this first. Then multiply each of these atoms by the subscript outside the parentheses. So you're looking at this multiplied. And then multiply each element's number by the atoms by the coefficient. Okay? So first, we're going to look at 2 atoms of aluminum times 2. So that means the 2 times a 2. So here we have a subscript of 2 by the aluminum multiplied by the coefficient of 2. That means we have 4 total atoms of aluminum. Here inside the parentheses, we have 1 sulfur, but there's 3 of those. So 3 times 1 is 3. But then multiplied by the 2 of the coefficient, we actually are going to have 6 S's. So S1 times 3 is 3, times 2 is 6. Okay, then let's do the O4. So in each of these little bits, we have 4 oxygens, but there's 3 of those sections. So 3 times 4 is 12. So we have 12 oxygens per molecule. but we have 2 molecules. So 2 times 12 is 24. So we have a lot of stuff going on here. So we have individual elements with their numbers or their subscripts. We have parentheses with subscripts, and they have a coefficient that gets multiplied by everything. There's a lot of kind of things to keep track of. Chemistry, especially when you get into high school, is a lot of math. But the good thing about that is it's easy to know whether your answer is right or not, because the math either works or not. In other branches of science, it's just kind of memorizing things, and you just have to know it. Where in chemistry, you can multiply things out and you can make sure the math matches. Okay. So I'm going to let you guys go through these. I think these are also on your notes. So you're going to figure out how many atoms you have total, and then mark it on your paper. There's a lot of atoms in these though. So 2 times 2, 2 times 4, 2 times 2, 5 times 1, 5 times 4, 4 times 4, 4 times 10. There's a lot. Okay, we're also not going to do that part. All right, so how can we use the periodic table to identify the atoms within a chemical formula? So we should know that the chemical symbol is what's on the periodic table. If we see those capital letters, then we know that's a new element and we look for the numbers. And then how can we identify the number of each kind of atom within a chemical formula? You're going to look for 3 things: the subscripts, the parentheses, and the coefficients, and then just start multiplying stuff around. So if you have questions, make sure you understand each of these bits. If there's any part in particular that you didn't understand, email, let me know, or we can talk about it in class.